Alright, so we're going to talk about continuity. So, in order for a function to be continuous, the following conditions must be met. So, first of all, this is within a range, okay? Within a range, 0, let's just say from A to B. In order for a function to be continuous between A and B, for every point between A and B, the function has to exist, and the limit also has to exist. That's number 2. And number 1, the limit has to match up with the function. So basically, every point here is directly on the line. Okay? So, is the cotangent of x continuous at the range 0 to 1? That's how it would be worded. Okay, first of all, in most problems, if they want to ask if a problem is continuous, if you know it's continuous, they will tell you if it's differentiable. If it's differentiable, so if they state if it's differentiable, you can say that it is continuous because the function is differentiable. Okay? But here, if we want to define continuity, we just want to see if between 0 and 1, are there any places that cotangent of x could be undefined. So we know cotangent of x, cos x, is equal to the cosine of x over sine of x. And when this is undefined is when sine of x is equal to 0. Sine of x is equal to 0 when x is equal to pi over 2, 3 pi over 2, negative of Joel, so I could just put plus minus, etc. And now, what this, and since between 0 and 1, none of these values appear, we can say that, yes, all the values exist. And that this function is continuous. So, yes. If it were to go to, let's say, pi over 2 itself, know that because we're using open-ended, it's still continuous because we don't include pi over 2. However, we said up to 3 pi over 2, we would have to say no because between 0 and 3 pi over 2, pi over 2 is not continuous. It does not exist because it's undefined. Okay, so let's look at these types of discontinuities. So we have infinite discontinuity. They are asymptotes. Whole or removable discontinuities. Basically, if the point does not match up with the limit here, so as you see, the limit does not match the actual point, or if the point does not exist, and you're just left with this hole where there's one spot where the function is not defined, and either side of it has a defined limit, then yeah, it's going to be a whole or removable discontinuity. Think of it as a violation of this first rule where the limit of f of x as x approaches a is not equal to f of a. Okay? And also, this is defined, but this isn't defined or is in a different spot. And then a jump discontinuity, this would apply when you would have the limit not exist, and potentially this would also not exist or match. So, well, you could say the same here, but know that this is only at one point and each side still has a defined limit that goes to a defined number. These go, asymptotes go to infinity in either direction. Okay? Now let's go to talk about squeeze theorem. So if you know that for each value of x at f of x, so let's just give an example. You can read that on your own. So let's say you have, this is your function f of x. Well, actually, let's say this is f of x. This is your function g of x. And here, you would have your function h of x. As you see, h is going to be always greater than or equal to g, and g is always going to be greater than or equal to f. Okay? And if the limit as x approaches a, let's just call this a. Wrong spot. Let's call this a. If h of x is equal to f of x, the limit of h of x as x approaches a is equal to the same limit on f, then we know that g of x also has to equal that same value because it is in between h of x and f of x. Okay? Now that we know that, we can solve this problem where, given that we know f of x is less than g of x is less than h of x, meaning we can apply squeeze theorem. Of course, if it isn't given and you're given functions f of x, g of x, and h of x, you would have to show it by solving f of x is less than or equal to g of x and rearranging the variables. But most of the time it should be given. We know that h of x and f of x and h of x are continuous, meaning that the limits match the values. Okay? But this isn't necessary because if they had the same limit, they can still, because if this was a hole here, it would still have the same limit. Okay, and h of 1 equals f of 1 equals 7. Find the limit as x approaches 1, the limit of g of x as x approaches 1. So here we would just state that, you would say that, let's see, because f of x is less than g of x is less than h of x, and then you would say the limit as g of x. Okay, I'm gonna have to handwrite it myself here. G of x. Here, the limit as x approaches 1 of h of x is equal to the limit as f of x as it approaches 1, which is equal to 7. Oh yeah, we're going to need the and there. Squeeze theorem guarantees the limit of g of x as x approaches 1 is equal to 7. Okay? Now we got intermediate value theorem. So think of the conditions is that f of x is continuous between a and b. So let's just call this one a, call this one b. Okay? Then an f of a is less than or equal to an f of a, and L, your target value, is between f of a and f of b. Then it's guaranteed that there's some point c, x equals c, that f of x will be equal to L. Okay? Now think of it as this. If you have a point here and a point here, no matter where you go, in order for you to reach this point from here, you would have to hit all the values between. Okay? So between these two lines, in order to get from this point to this point, you would have to hit all the y values in this range. This can be proven because if you try to, let's say you will try to go all the way up and go down, you still hit all those y values just very early on. Same thing, you try to go down and up, it's just hits later on. Sorry, it's a bit hard to see. Because just know that because of how continuity works, you have to hit every single number in between f of a and f of b. So if L is in between that means it's guaranteed that it would exist between that a point C, a point with x equals C would exist with that would be equal to L. So in our example, does does f of x equal 8 between x equals 4 and x equals 10, given that f of x equals 3x minus 4. So first of all, we want to state that because, okay, look, this one you can actually just write. Okay, let's try to expand that because f of x is continuous in the range. Well, you can say infinity, negative, and if you will want to use the symbols here, and well, actually, you would rather than just say that, you just want for one. You would probably put the range since this is technically correct. Continuous between 4 and 10. Um, and let's see, you would have to plug in 4, so that's 12. 4 minus 4, that's 8. Is less than or equal to 8, less than or equal to, you plug in 10, 30, 26. IVT guarantees f of x equals 8 between x equals 4 and so between 4 and 10. I believe, yeah, in that range, 4 and 10. What is that? Okay. Lastly, just some special limits. So basically, anytime you see sine of x over x is equal to 1, tan of x over x is also 1, as x over to 0. So basically, in any of these, you would just want to try to balance it by adding. So, for example, you had the problem 3 sine x over x, sine x, or not sine x, x squared. You can just simply add another sine of x, add another sine of x down here. This is just going to be equal to times x. You find the limit as x approaches 0. These, each sine x would just cancel out to 1 each, and you're just left with 3 over sine of x, and that would just be undefined. Right? Let's see if when sine equals, wait, hold up, wait, I think I did something wrong earlier. Yeah, wait, see, yeah, sorry, this should be 0, pi. Yeah, so actually, yes, but this point is this graph is still continuous. I would have lost points because I showed the math wrong and had the wrong reasoning, but note that x is equal to 0, pi, and that's when sine of x is equal to 0. But because it's between 0 and 1, because it does not include 0, it's continuous. Okay, cleared that up. So yeah, that would be undefined there. And I believe that's it.